And then we try to connect all. These are our habitat with weather and climate plus local features. Brian talked about heat before. And Brian explained, also Wei Yan, how to connect, how to capture this variability into the organism. And then through body temperature and then also the available food. The available food is essential for the life, because if we have sufficient food, we can reproduce. If we don't have food, just very probably we die. And then we we try to capture this variability and translate it from the side of the organism as functional traits and its effect on functional traits. And then we, well, and then once we have characteristics of organisms, we need to we are able to estimate the life history traits affecting the population dynamics. We usually, or we are doing in this period of the life, we are doing it using a mechanistic approach, just a mechanistic model, and I'll explain why and how. This mechanistic model is just called a dynamic energy budget model. Through the energy budget model, we can estimate the body size and fecundity of every organism. But we know that these characteristics are the main determinant of all components of population dynamics. And then body size and fecundity are able to affect dispersal, larval mortality, and which are components of propagule pressure. And then we can try to get information about the presence of every organism in a certain place and its role inside the community. If you, usually we try to capture to capture the variability, environmental change, environmental variability, just to connect to through statistical methods to connect it to the local presence of species in the community. Instead, we propose to have a longer path just to use the power of a mechanistic approach and the magnitude and the changing of functional traits and life history traits just to provide more realistic models, prediction about the effect of climate change or environmental change just on the ecological response and then effects on biodiversity. The biodiversity. We don't want to exaggerate, but we can also infer on the effect of biodiversity just on biophysical response as through biotic interactions. This is the core of this framework. This model is the dynamic energy budget model proposed by Buzz Coleman in 18, right? Yes. And in last version, just in 2010, in a book, in a recent book, this model is a bioenergetic model, is based just on the flow of energy coming from the habitat and fixed into reserves, and then used for growth and reproduction. And the most important concept is that the bioenergetics and this model is based on this definition, because one way to think an animal is just as an energy processor, because it acquires energy from food, from its environment, allocates this energy among maintenance, growth, and reproduction, and then a part of this energy is converted just in eggs and structure, and then growth and reproduction. I don't know if you never heard before the concept of scope for growth, but this model is different by scope for growth because is based on, introduces the concept of reserves, and then the idea is that the food is assimilated and accumulated in stored in reserves, and then as a function of some characteristics of the organism and the environment, it can allocate to maintenance to different functions, and then maintenance of structures, and then growth and reproduction. This model introduced the concept of an allocation rule, because this allocation rule is called the key rule, or kappa rule. This means that when the energy is mobilized from reserve, every organism has a very specific way to allocate the energy to growth and maintenance and reproduction. This is space specific, and in theory we can measure it, and then we can use it also for evolutionary studies, for example, or we can this model is easy and useful because this is stolen by Brian by Heteroclim also, because it's possible to use this model just to do a sensitivity analysis, just to explore a different environmental the effect of different environmental components on the fitness of organism, for example. These are the outputs that we saw before, are the same for the DEB model. Life history traits that we can estimate through the DEB model are the body size, the growth rate, the number of eggs per lifespan, and so on. But before, to understand how to apply the DEB model and just to use this mechanistic core to try to capture the environmental change variability to the community and population dynamics, we need to know how each species works, because every species works according to specific rules. This type of step is usually called parametrization, which is based on the idea that we need to get the standard parameters of functioning of every organism. For example, we can use usually we use the respiratory science since you know that the oxygen consumption is a good proxy for maintenance costs, we use the respiratory science just to fix how one organism works. For example, as a function of temperature. And then we can use the respiratory science and then the oxygen consumption just to understand how metabolic rate varies and scales with temperature. And in normal our experiments, we measure the oxygen consumption rate of every organism organism at different temperature, just to try to get the curve, the tolerance curve, which is very similar to a normal curve like those described by Gray-Williams yesterday. We use also the heartbeat rate, and which is another measure, just another proxy for metabolic rates. And then the apparatus is very simple. Probably the measure is less reliable respect to the oxygen consumption rate, but probably is easier to do it at different temperature with a lot of different replicates. And then in this case we can increase the number of replicates just to reduce the variance around means, and this means that we can get the very good measure of metabolic rate as a function of temperature. This because both rates as a function of temperature, just to get the Arrhenius temperature, which is the slope between deriving from this regression, putting the temperature, the inverse temperature in Kelvin on the x-axis, and the logarithm ln of oxygen consumption in y-axis. And then the Arrhenius temperature is just just that value indicating how our organism works as a function of temperature. And this just an application with our muscles. This is an example with Mytilus gallo-provincialis, Methylaster minimus, Brachydontes pharonis, three species just colonizing the Mediterranean. Mytilus gallo-provincialis is also a colonizer of your coasts in some parts, and the Pacific coast of the US. And you see that depicting the functioning of every organism as a function of temperature, we can have different way to cope with the thermal variability. There are animals like Mytilus gallo-provincialis, which are able to face a very large range of temperature. Or we are, for example, the case of Methylaster minimus, which is very small and is just endemic from Mediterranean. It has very small breadth of his thermal tolerance. This Brachydontes pharonis is a species coming from the tropical, yes, from the Southeast Asia. I know, Gray, that you don't know Brachydontes. You only limpets. That's fantastic, as you say. And then you can gain information about these animals. Is a totally different respect other animals, and then we can infer. This is a quantification of the ability of this organism to colonize different kind of habitats. Another important component of our mechanistic models and of our approach is how organisms relate with food, with the habitat of through food. Usually in the DEB model, in general, we use the functional response just to describe the ability of animals to get food from habitat. In the DEB model, we use the Holling type 2 functional response, which is this type of functional response, and it derives from putting on the x-axis the food density and in the y-axis the ingestion rate at different increasing food density. This is a very important information because we can get from this information the alpha saturation coefficient, which is the food density at which the ingestion rate is the half of the maximum. This xk, the alpha saturation coefficient, changes with the quality, for example, of food, is an expression of the handling and searching of food, and then is a very good way to understand how our organism relates with the habitat. These are always our Mytilus galloprovincialis, Mytilraster minimus, and Brachydontes pharaonis. You can see that from this observation we can also understand which is the trophic degree or trophic status of in which every species reaches the maximum incoming of energy, just explained by the functional response.